we just expand the classification of premixed burning as three categories. One is the so-called explosion. The other two is a combustion wave, and the speeds are lower than the sound speed or higher than sound speed. We call it deflagration wave and also detonation waves. Now we more focus on the introductions on the deflagration waves in premixture. Okay, as we understand, I already explained how to describe the burning condition for the premixtures. You think about for the methane react with oxygen. This is a pure oxygen. Ideally, then you can think stoichiometric burning means you convert your hydrocarbon fuel and oxygen to the carbon dioxide and water completely without any fuel and oxygen left. Then we say this is a stoichiometric burning. By this chemical formula, they tell you the stoichiometric burning can be expressed as the mole ratio 1:2 or mass ratio 1:4. As this is a base, for example, here we can define the so-called equilibrium ratio for this methane burning with pure oxygen, and they use the stoichiometric condition as the references. Then you can define the ratio for the equilibrium ratio smaller than 1. We call this as a limb mixing, because the fuel is less than the oxygen supply for complete burning. When they equal to 1, they simply tell you it's just a stoichiometric burning. But if the phi larger than 1, equilibrium ratio larger than 1, that means that you have too much fuel compared with the oxygen need to be consumed. And you can see this as a simple definition to understand the burning will occurs in three conditions. One is the limb burning, means the fuel is less, then you will have an oxygen depth in the combustion process. And a rich burning means you have too much fuel, then you will have an excess fuel depth out in the downstream of premixed burning. Stoichiometric burning simply tell you they are completely burned out all the fuel and oxygens. And this is a typical example for pure oxygen. But basically, I already emphasized in reality, you can think about oxygen coming from the air, then you should bring the exact composition of air into your chemical formula and redefine it. And you remember the stoichiometric ratios, burning ratios for methane burning in air is around 9.5%. Basically, I always use this methane burning as an example. You need to understand and remember this number. Now, first step, we try to think about the flame structure, including the flow structure for given premixed flame. Here, this is a typical plot for you to understand. I will use the slides to show you step by step, but in general, I give you the understanding on this picture at first. Here, you will have a stationary premixed flame exit here, and you will find out you can the flow structure can be divided by different regions. One region is far away from the flames. We call this as the upstream regions. Then you will move. If you move from the left-hand side to approaching to the premixed flame, then the upstream side will becomes you will approaching to the so-called the preheating zone. Then go to the reaction zone. Later on, you will move to the downstream region. Now I try to give you a more detailed understanding step by step by using the slides. Okay, the similar plot here, and I will explain it one by one. Okay, here you think about, suppose you will flame propagate, in this case, from the right-hand side to the left-hand side continuously, right? But now we hope this friend will sit at a certain position, then you can do some measurement on flow velocity or temperature to figure out the detailed flow structure near the premixed frame. The only way is I just mentioned how come you can make this frame sit at a certain position without moving. Simply, you need to supply suitable or enough strength of premixture, and those premixtures supply will balance with the consumption of your premixed frame. When they are balanced, then you will sit, right now this frame will sit at a certain location. Under this consideration, you will figure out, as I explained earlier, the frame speed can be determined by the supply velocity from the upstream side. Okay. Now you figure out the frame can sit in here, then this blue region represents the visible frame. Usually for premixed frame, show you the blue color, then I will give you the blue color to represent the location of your premixed frame. And here you can see in the very far upstream sides, this is represent the temperature profile, okay? And here there is the, we call this as an upstream low temperature region, okay? Why we call this is an upstream cold temperature region, because away from the premixed frame, here you can see temperature is quite low without too much change. Supposedly, here you're starting from the room temperature, and this room temperature can maintain for a certain distance when they approaching to the premixed frame without any variations. Then we call this region is upstream low temperature region. And later on, you will find out when they're approaching to a certain boundary. Here, this is a boundary, and the temperature start to increase. And in these regions, temperature continuously increase, and we call this the so-called the preheating zone. And when the temperature move into the very closer to the visible frames, then we say we move to this is a reaction zone. After chemical reactions, when the flow passing through the premixed frame, then later on you will find out the temperature will remain a high temperature. Okay, then we call this the downstream high temperature zone. Depend on the temperature variation, you can separate to distinguish the behavior, flow behavior in these four regions. One is the upstream low temperature region, the other one is the preheating zone, and the major one is the reaction region, and finally is the downstream high temperature zone. Now you can see in the preheating zone here, before the preheating zone, then we go back to see the downstream low temperature zone. In the previous time, we used the temperature profile to define different regions. And in different regions, you still can see the concentration of fuel and oxygen, they are changed. But in this case, I just tell you there is the two, it's easier to identify because you may burn different kinds of conditions, rich or lean, right? But in this plot, I just tell you, for example, if the reactant is deficient, it's a small one compared with the other one, we say this is a deficient one, the concentration of the deficient reactant will go this way. Okay, in the upstream side, because temperature is low, then they do not have thermal decompositions. Until the temperature increase, and if you move to the preheating zones, then the reactions, the thermal pyrolysis decomposition occurs, start to dissociate, then they move to the so-called preheating zone. Similar way, for the abundant reactants, they always keep the same concentration in the upstream sites. But both of them, they will be reduced in the concentration will be reduced in the preheating zones. This is the preheating zone. And finally, they will move into the reaction zones, okay? Because now you have some decomposition of original fuel, for example, methane, then they try to produce a large amount of CH radical, OH radical, or maybe the H radical. And in this region, in this preheating zone region, you will find out temperature is increased and also concentration decrease. When they reach to the boundary of the preheating zone and the reaction zone, actually this boundary is defined by so-called ignition temperature. Means now since you have a large amount of active species, then they will start to the temperature go to high enough ignition temperature, then they start to have a recombination reactions. Now you can see in the reaction zones that this plot, this line tell you the chemical reaction rate. They will increase very fast, driven by the Arrhenius law, and suddenly they will reduce to zero because the complete recombination chemical reactions. Then all the intermediate species convert to the stable products. And these regions, basically, we call this the so-called chemical reaction zone. The thickness of chemical reaction zone is relatively thin compared with the thickness of preheating zone. You can see it's a different scale. Okay, the thickness of preheating zone is much larger than the thin zone for chemical reaction. From our experiment, for the laminar flame situations, the flame thickness for premixed flame is usually around 1 millimeter to 2 millimeter. Usually it's around 1 to 2 millimeter. They can complete the chemical reactions in the chemical reaction zones. And finally, you can see, since this is a premixed burning, all the small reactants will be complete consumed, then you will reach to the zero. Okay, now but the abundant reactant, they still have some excess reactant that remain, but since they do not have the other one to react together, then they will keep the scent continuous in the downstream region. Okay, the boundary of your reaction zone in downstream basically defined by the completion of deficient reactants. Okay, and here you can have some abundant excess reactants exist in continuous in the downstream sites. And you can find out additionally, because all the reaction complete, the heat of combustion release and absorbed by the mixture itself, then the temperature will reach to highest point. Usually at this point, we say this is a flame temperature, or in the adiabatic case, we call this is an adiabatic flame temperature. And finally, we will look at the continuous to the downstream sites. In the downstream side, the temperature and also the concentration will remain constant, continuously move to the right-hand side for this one-dimensional flow. This is a simple mechanism to describe the flow structure and the flame structure along the coordinates point to the flames. This is just give you the physical idea about those kinds of structure. And here, this is a so-called one-dimensional flow structure. But for the general application, later on, I will give you definitely there is some modification on those kinds of concentration and also temperature distributions. But anyway, in this case, they tell you, since all the chemical reaction complete in the chemical reaction zone, heat release, that means the temperature will reach to the maximum flame temperature. In the case in downstream side, if you do not have any energy loss, heat loss, the temperature will keep the same. And this line is a horizontal line, represent a adiabatic condition, and they will approach into they will remain and maintains adiabatic flame temperature. But in all the case, there is the heat loss in the downstream side by radiation or heat conduction, any kinds of heat transfer, then the temperature will reduce. This is a real one. The temperature will continuously reduce. Sometimes even increase, because I will give you the example for the jet premixed flame. Since there is the buoyancy effect to push the high temperature products move to the upward, they will force the heat penetrate or concentrate to the downstream side. You may have temperature higher than the original flame temperature in this case. Okay. Now, in general, when you look at the flame structures, you can see there is the so-called the visible flame, and usually it's the blue flame. How come you can see the blue flame? Actually, how in the reaction zones, especially in the very downstream region of the chemical reaction zones, they accumulate so much amount of the carbon monoxide and oxygen hydrogen radical and carbon hydrogen radical. Those radicals will emit light more closer to the blue, to the violet. Then you can see those kinds of flame color coming from the emission of those intermediate species, CO, OH, and CH radicals. Then this is a typical example to tell you when you see the blue flame means that at that zone, temperature high, and also has a large amount of carbon monoxide and OH radical and CH radical. The other way, in the downstream side, you have a large amount of carbon dioxide and water, which means they are products, right? When those products, carbon dioxide and water exist in the downstream, they will emit the red light. I give you the example. As you remember in our previous experiments, I hope you remember there is the so-called the stagnation point flow, right? This is the cold flow we have. And in this experiment, actually, for the cold flow experiment, we apply water particle into the mixtures, and those kinds of pictures taken by the camera actually basically coming from the reflection of the reflection of the laser light from the water particle. Okay, which means that now we apply the water into the cold flow, then you can see a very nice straight line on the pictures. Now, if you eliminate the water application and simply supply the methane mixed with air, then you will ignite it and you can have a very nice so-called premixed flame. This premixed flame, I tell you why you can have this very nice stagnational and planar flame, because you supply enough flow velocity, and those velocity just give you the enough supply of premixture to support the consumption of the premixed flame. Then balance, then the premixed flame will sit at a certain position. Okay, which means I try to emphasize again, what is the meaning of propagation velocity, the premixed flame? They are simply tell you the flame speed or propagation speed represents the burning strength of your premixed flame. If the burning strength of your premixed flame is strong, that means the propagation speed is very fast. If the burning strength of a premixed flame is low, is small, then actually the premixed flame burning will propagate at a lower speed. Okay. Now the burning strength of premixed flame can be represented by flame speed. Actually, data simply can be related to the supply of your premixed flame or premixture, right? If you can supply a large amount of premixture, then this stronger premixed flame can be balanced, and then they can sit at a certain position. In case if you do not supply enough premixtures to this stronger premixed flames, then this stronger flame speed will propagate to your supply port. Okay, then we call this the so-called flashback. Later on, I will tell you those kinds of imbalance between the burning velocity, the flame speed, and also the supply velocity. By the way, I need to mention some people will use the different kinds of terminology to describe the propagation speed, right? When I say the propagation speed, actually they are completely the same with the flame speed, but in different physical emphasis. Flame speed means that we just talk about the magnitude of the burning speed. Okay, but propagation velocity means there is the velocity. Actually, there is the direction. Okay, when you are dealing with the velocity, then you will think about the magnitude and also the direction of the propagation wave. Okay. Now, this is a very simple experiment. The first one, this is a cold flow involving with the water, right? And on the right-hand side represent simple burning of the premixed flame of methane and air. In this case, since we are working on the burning, then we do not apply the water into it. But the next step, we try to actually, I will give you the example from this experiment to tell you the velocity variation and also the temperature variation along this frame. And when we do the measurement on the flow velocity, actually you need to apply certain so-called sealing particle. That means that now the next step, I apply water into the frame. Now the most important thing is now if I apply the water, so many tiny water droplets accompanied with the mixture of methane and and air, then you will find a very nice picture here, right? Here in the upstream side, compared with the cold flow, actually they do show you there is some water coming in and they represent so many straight lines. Actually, it's a path line or track line because this system is a steady. We operate in steady conditions. Now you can see a lot of water coming to approaching to the premise frame, and here you can see there is a layer, a reddish layer that occurs in the downstream, right? And from the experiment, we try to figure out how come the frame from the original one then they have additional reddish color in the downstream side. Now you will figure out when you move your laser light to the downstream, and you can see there is the water passing through, and definitely they show you why you will have the so-called reddish color, because in this downstream side, water passing through the frame because the temperature is high, then they will promote the evaporation of water, and they will produce the more water vapor in the downstream side. In the regular burning here, the upper frame, the concentration of CO2 and water is not too much to enhance the emission or the the strong color. But in this case, because we apply a lot of tiny water, then they will produce so much amount of water vapor accompanied with the productions from the chemical reactions. Then the concentration of water vapor is high, and they will show you the reddish color. Okay, this is another point I want to mention. In the combustion process, when you see the red color, usually they tell you in that regions contains a large amount of water vapor. When they accumulate, then they will reflect some color, some reddish color, and then you can look at it as the water concentration higher. And for the blue color I just mentioned, they show you there's a lot amount of concentration of the CO, OH, and CH radicals. In many cases, you can see the yellow color, right? And I already mentioned when you look at the flame color being yellow color represents in the flame zones, you have a lot of a large amount of carbon particle aggregation of carbon particle in that region. Okay, now and you can see, for example, for the normal fire occurs for a house, right? They usually show you the reddish color and also the yellow color, because when your house under fire, and always our buildings, those kinds of combustible materials contain certain amount of water, and in the fire process and the fire extinguishment, they apply water into the fire field, then you will accumulate a large amount of water vapor. Then the color in the burning zone will show you the reddish color. Okay, and this is a typical observation from our experiment to tell you how to identify the concentration of the of your flow or the gas inside the burning process.